Lecture of Andrea. You wrote us the reminder from yesterday.
Okay. Thank you. Yeah, so this is a reminder of what we started doing at the end of last lecture. We convinced ourselves somehow that it's interesting to look again to ridge regression. So I wrote here the definition of ridge regression. You have a design matrix Z and a vector of responses, and you minimize least square plus a penalty. We are interested in the prediction error, in the test error, or the excess risk that I wrote here. And the way I define it is that I take expectation over the noise in my data and the observation of the new sample point, and this is the prediction of the new test point, and this is the truth at the test point. And I mentioned that this risk you can write explicitly as a sum of a bias term and a variance term. And the bias takes this form, and the variance takes this form. So they are a combination of the metric sigma. Sigma is the empirical, the population covariance. So this is E of Z1, Zi transpose. And sigma hat, which is the empirical covariance. So this is the covariance of my feature vectors. And then this S matrix that is basically a resolvent. Okay? And there is some formula that you can derive yourself very easily with linear algebra. Okay, so today what I want to do is, the first thing that we want to do is derive a formula for this. Actually, I will not do the derivation, I will just state it. So one can derive sharp, I don't know how to call it, characterizations. For in the proportional regime. So what I state is, so there is many results on this. I state one result that is in a paper that we wrote a couple of years ago, and the assumptions there are the following. The Zi, I'll take the Zi to be sigma 1/2. So Zi are the rows of the matrix Z. They are IID and they are sigma 1/2 times UI. Okay, where the UIs have IID entries. Okay, with mean 0, variance 1, and okay, and you need some moment condition. Let's say 8. Okay, and we need some condition in this result on the eigenvalue of sigma. So I will assume that lambda max of sigma is less than a constant, and is less than a constant. The sum of the inverse of the eigenvalues of sigma is less than a constant. So in particular, this is satisfied if the minimum eigenvalues is bounded away from 0. And so, okay, we'll state for results for lambda equal 0 plus. Okay, so basically the minimum norm interpolator, but okay, you can look at the paper for the more general case. So these precise conditions are in a paper with Hesty et al. And the characterization goes like this. Okay, let lambda star be the unique solution of the following equation, n equal trace of sigma plus lambda star identity inverse. Okay, so what is this? It's a function of lambda. I have the function of on the right hand side. How does it behave? Well, at lambda equals 0 is equal exactly to p, and then at lambda goes to infinity goes to 0. So this is f of lambda. And then you look at n. Let's say that p is bigger than n, and then I take this value, and this is lambda star. Okay, so this lambda star will play an important role, and now I'm out of space, and then define in terms of this lambda star two quantity. I'll call it VNTH and BNTH. So this is sigma square over n, and then there is trace of, okay, perhaps I'll write here these formulas. This is trace of sigma square over sigma. Oh. I erased exactly what I wanted to. Okay, now I erased the B and so let me rewrite. This is B. Let me write just at least this. Okay, so these are, here there is the real bias and variance. And this is kind of the prediction for them. Okay, and the theorem says the following. Let's say I can make it more precise, but with high probability, Bn minus Bthn is less or equal than n to the minus, I think, 1/6, and Bn minus Vth n is less or equal than n to the minus 1/6 times some constant. Okay, let's probably. Okay, so this is saying the following. Assume that there exists a constant c, a numerical constant, 1 million, such that this is true, this is true, this is true, this is true. Then there is another constant c bar that depends only on this c, such that this bias and variance are very well approximated, or they are well approximated by these theoretical predictions that are given here. Okay? This is for any matrix sigma. So perhaps I'll pause a moment because then I want to, so let me perhaps say a word about, I will not prove this theorem, but it's some random metrics theory calculation, and it uses, I mean, the way it's proved in this paper, we use something that is called the anisotropic local law. In particular, a non-asymptotic form of this that is proved in a paper of a few years ago by, I think, Knowles. Okay, so what is an anisotropic local law is basically a statement about V as lambda V. So matrix elements or matrix elements of this resolvent matrix. Typically, in random matrix theory, the first thing that you study is the trace of this object. Okay, the trace of the resolvent. This is the Stieltjes form of the distribution of eigenvalues. But something that is also interesting and that there are results about is instead sandwiching this between two vectors. And for fixed vector W and U, study this object, right? And then, okay, there are results about this thing, and you understand that this kind of thing is very useful because this is the structure of this bias that you have here. Okay, so I want to, rather than spending time in describing the proof of this, I want to spend time trying to discuss the interpretation of this result. But before that, perhaps I'll stop to ask if there is any question. I mean, does everything that I wrote make sense?
Yes, maybe that goes to the interpretation. But so B is proportional to lambda squared, but you send lambda to 0. So what is the mechanism this actually is not becoming 0?
Right. So you see, this is the solution of this equation, right? And so, at least formally now, why intuitively this happens is non-zero. We can talk about it, and I will talk about it. But you see that even if I start with lambda equals 0, lambda star will be different from 0. Now, if I look at the equation for lambda different from 0, you get something like 1 minus, I think, lambda star over lambda here. Okay. I think I remember correctly up to this multiply, whether here this multiply n or not. But in any case, this changes this thing in the sense that this dashed line now becomes, instead of this, becomes something like this. But not much changes. Okay, so here you have to equate this lambda over lambda star. So you have to equate this to something like this. Okay, so this makes lambda star grow a little bit to put a lambda different from 0. But as you let lambda going to 0, so if you look at this equation, the right-hand side that I plotted is this object. This is the curve n times 1 minus lambda over lambda star. Okay? So for lambda different from 0, lambda star grows a little bit, but as you let it to 0, it stays non-zero. Okay? And you see this is an effect of the fact that p is larger than n. Here this value is n. If p is smaller than n, then lambda star goes to 0 as lambda goes to 0. Okay? But actually the fact that lambda star is non-zero is one of the most important things.
C bar is independent of the ridge.
C bar.
The bound constant.
It's independent of the ridge of the regularity. So this statement is for lambda equals 0, right? So, yeah, so this is in, this statement that I gave here, there is no lambda, so lambda went already to 0. Now, there is an equivalent statement for lambda positive, and you get better exponent here. Now this exponent here is suboptimal. You would expect this exponent to be at least 1/2, but this is an artifact of the proof. For lambda positive, the same paper has a proof with lambda, with this exponent equal any 0.49. Okay? But as lambda goes to 0, we need to do some approximation.
So maybe another question, kind of in which sense is this a theory? Because the only thing you did, you kind of got rid of these empirical covariances and
right. So now, now everything of this is purely in terms. So these are deterministic things. Lambda, sigma is deterministic, beta star is deterministic. So these are deterministic objects. These are random objects. And okay, of course, you can always think that sigma is diagonal, right? You can rotate it in the base of the eigenvector of sigma and write everything in terms of the eigenvector of sigma and the component of beta star on the eigenvectors of sigma. It's obvious this. And so all of these matrix element and traces reduce to sum. And if you want, you can take, if you know the limit of the eigenvalue distribution, you can take the limit. So for instance, this thing is sum over I of sigma I square over sigma I plus lambda star. And this is sum over all the eigenvalues, okay? And if I divide by p, this will if the distribution of eigenvalues converges to a limit, this will converge to a limit, as p goes to infinity. But I think it's not necessarily useful to take a limit. So you can write this as a distribution, an integral over rho d sigma, where rho is the distribution of eigenvalues, sigma square over sigma plus lambda star. This is what physicists like normally to do, right? They take the limit p and then to infinity and write everything in terms of an asymptotic distribution eigenvalue. I don't think this is more useful than this. Actually, I think this is more useful than that. Okay? And of course, if now sigma, the distribution eigenvalue, takes a simple form, then this becomes very simple. But, okay, so I think that, okay, now I want to let me talk about interpretation of this result, and not of this result, really, of these formulas. What insights can we get from them? And let me start by noticing, we have this big denominator. I want to get rid of it. And notice that 1 over n trace of sigma square times sigma plus lambda star I square minus 2. This is less or equal than 1 over n trace of sigma times sigma plus lambda star I minus 1. Okay, better. Okay, and if you look at it, let's go back to the case lambda equals 0. This is exactly 1. Okay, so this object here, as it should be, is less than 1. So let's assume that is less than strict 1 minus 1 over constant. In fact, in many cases, it's easy to show that it's strictly bounded away from 1. So let's say that is less than 0.9. I will not go into proving that. Then what you get is that the theoretical prediction for is sigma square over n times trace is, okay, it's not equal, but less than a constant, C0, times sigma square times sigma and the theoretical prediction for the bias is less than times Now, if you look at it, these formulas are basically identical to this one. So remember that S lambda is lambda I plus sigma hat minus 1. So this formula is exactly equal to this one, apart from the constant c, except that I replaced lambda by lambda star and sigma hat by sigma. Right? This guy, there is one sigma, and then there is an S lambda that is exactly equal to this guy. And this formula is exactly equal to this, right? There is sigma square, that is sigma sigma hat, and then S lambda becomes lambda plus lambda star I minus 1. Okay? So these are the bias, the right-hand sides, apart from this constant C0, so these are bias and variances for the following sequence model. How do I want to write it? So ys equals sigma 1/2 beta star plus sigma over square root of n w, and beta hat s equal argmin of ys minus sigma 1/2 beta plus square plus lambda star beta square. Okay? So what I'm telling you is that, up to this constant C0, the variance and bias of the original model are equal to the bias and variance of a simpler regression model in which you observe beta star, but the design matrix is just the population covariance, and then you run a ridge regression, but the regularization parameter is not lambda, is lambda star. Okay? So what happened somehow is that we started from x random, z random, the design matrix random, and regularization 0, and we ended up, this is equivalent in some approximate sense to design matrix sigma 1/2 that is deterministic, and regularization parameter lambda star that is strictly positive. Okay, so this is an interesting phenomenon. So why is this called the sequence model, or I call it sequence model? Because, as I said before, you can always think that sigma is diagonal. So it's equivalent to observing, each. So it's equivalent to a model in which I observe ys1 equal sigma 1/2 times beta 1 plus noise. Okay, this is sigma of the noise. I'm calling sigma I is the eigenvalues of the covariance, and sigma of the noise. Okay, so it's equivalent to a model in which we observe separately the p coordinates of beta in the basis of eigenvalues of sigma. Yeah.
So you only got an upper bound here.
Yeah, it's true. That's true. It's true. I mean, here I get an upper bound, but on the other hand, this is always less than 1, right? So this guy is, I'm assuming that is less than 1 minus C0, and is always bigger than 0. Okay, so this denominator is bigger than 1 over C0 and less than 1. Okay, so this is true up to constant. If you allow me to make this assumption, and again I claim that if you assume something about the eigenvalue decay of sigma, that assumption is correct. Okay, so, okay, now, of course, I want to understand now what is the behavior of lambda star. So as from this picture, you would imagine that as n gets larger, this lambda star, so lambda star becomes smaller. So lambda star is decreasing in n. So I'll be a little bit heuristic here, or very heuristic. So let's say that lambda star is small. So the hypothesis of my heuristics is that lambda star is small. And let's say that you take a covariance in which the eigenvalues, so these are again the eigenvalues of capital sigma, decay to 0. Okay. So if they decay to 0, so the eigenvalues will be 1, 2, 3. I can find a lambda star sits somewhere here. I can find a k such that sigma k is bigger than lambda star bigger than sigma k plus 1. And in fact, since this decay to 0, this difference will be very close. So I can assume perhaps that lambda star is very close to sigma k. So I'll define k as the last k at which sigma k is bigger than lambda star. And since these eigenvalues go down to 0, this will be very close to sigma k. Okay, so now let me rewrite kind of approximately this equation, in this setting. So if you look at this equation is saying n equals sum over L1 to, let me write P, or let me write infinity, doesn't matter, of sigma L over sigma L plus lambda star. This is the equation. So I can break down into the sum up to k and the sum after k. In the sum up to k, lambda star you can consider it negligible. It's not really negligible, but it's within a constant of this. So this is approximately, use this symbol, k. So for all the L up to k, this dominates. Lambda L dominates over sigma star, so you get 1. And for the one after that, what you get is 1 over lambda star, which is approximately 1 over sigma k, times the sum over L k plus 1 to infinity sigma L. And use this symbol to mean that the two sides are equal up to constants. All right, so let me call this, I'll give a name to this. So this is the effective rank, right? This is saying, imagine that all the eigenvalues after sigma k are either of order sigma k or they are 0. This is equivalent to how many eigenvalues do you have? Right? If all the eigenvalues, if the eigenvalues, so you have sigma k, this is the decay of eigenvalues of sigma k, k. If all the eigenvalues after sigma k were either all very close to sigma k or 0, this ratio would be exactly equal to the number of non-zero eigenvalue. So you can think of this as an effective rank of at level k. So let me give you a couple of examples. Let's say that sigma k goes like k to the minus alpha for some alpha bigger than 1. Alpha bigger than 1 because I want the norm of these feature vectors to be finite. Then what you get, okay, R1 of k, you have the integral of k minus alpha. Okay, so this is what is the same as 1 over k to the minus alpha times the integral between k and infinity of x to the minus alpha dx. And this is of order k. So in this case, these two things are of order k, and so k is of the same order as n. So in other words, my regularization parameter, my effective regularization parameter, is the same order as the nth eigenvalue of the empirical covariance, of the population covariance. So this is one example. Let me give you another example that might seem more exotic. Okay, and the other example is the following. Let's assume that sigma k is k minus 1. So this is the borderline case of this. And to make it summable, I put log k to the minus beta for beta bigger than 1. So you can do, okay, it's very easy to do your calculation here. And what you get is that the effective rank goes like k log k. So in this case, in this equation, this term dominates this. So the equation reduces to k log k of order n. And so you get that k is n all over log n. Okay, so this is the second example. Okay, now I erased what I needed. Yeah. Well, because next thing there will be, you can define this with another exponent, right? You can put here an exponent p. Here you would have p. It's just my notation. It's not a universal notation, so don't take it seriously. Okay, so very nice. So now we have an understanding of this lambda star. So now, if you remember, I'll rewrite the formula. The formula that I wrote for the variance was that up to constants, this is sigma square over n trace of sigma square over sigma plus lambda star I minus 2. And I can repeat the same game as before. Now I realize that this sigma and sigma square. Okay, in any case, this is the same as sigma square over n. And then I split into the eigenvalues larger than lambda star and smaller than lambda star. So the largest than lambda star give a contribution that is k. And the other one give a contribution that is 1 over lambda star, so 1 over sigma k square, and then sum over all L bigger than k, sigma L square. Okay, so you could call this R2. of k, but you can convince yourself, since all of these ratios are less than 1, this sum will be, in general, much smaller than this sum. So, okay, let me say that in many cases, let's take it k sigma square over n. This is not quite true, but you know, in this two model, this is roughly the same. Right? So I will, you know, there are cases in which this is not negligible with respect to this, but in these two cases, this is of the same order as that guy. You can do your computation. So k, you know, this is the same as the variance of linear regression when you have k parameters. Here we have p parameters that are much larger than n, but the variance doesn't scale like p. The variance of, you know, if you had an identity covariance, perhaps I should say that, if you have an identity covariance, this becomes of order p, typically, if lambda goes to 0. And no. So this is really the number of degrees, effective degrees of freedom in your regression. Okay, now I can do the same for the bias, the same calculation for the bias. Okay, let me start it here. So again, the bias, what was the bias? The bias, this was, we said, up to constant was lambda star square times beta star times sigma plus lambda star I minus 2 beta star. And now again, up to constants, I can go in the basis in which sigma is diagonal. So you get sigma k square. This is for the lambda star square. And then I get sum over all, for all the L less than k. You get, let me call beta bar L. This I call the component, the coefficient of beta star in the health coefficients in the basis of eigenvectors of sigma. So beta bar L is VL times beta star, where VL is the health eigenvector of sigma. You have this square, because, and then you have this 1 over, there is a sigma at the numerator and a sigma at the denominator, so sigma L here. And then there is the component, the part of the beyond L, right, beyond k, so sum over L bigger than k, and then beta bar L square, right? And then in this case, I can neglect this sigma with respect to lambda star. So you get sigma L over sigma k square. Okay, and now, okay, let me just massage this. Sum over L less than k, and then sigma k square over sigma L. Okay, beta bar L square plus, and then sum over L bigger than k, sigma L beta bar L square. So this tells me something very interesting, that what this piece is telling me that I'm not fitting at all the projection of beta star onto eigenvectors after k. This is the same as beta star projection bigger than k sigma projection bigger than k sigma. Beta star, right? Where p bigger than k is the projection onto, the subspace spanned by eigenvector after the kth one. This is exactly the same, right? and, or in other words, this is, projection bigger than k beta star square, right? Sigma norm. Remember that what we are computing here, the whole risk is beta lambda hat minus beta star sigma norm, right? So this is what is telling you is that of this part, you can always write it as projection less than k, beta hat minus beta star, sigma norm square, plus projection bigger than k, beta hat minus beta star, sigma norm square, right? This is the risk. The prediction error is this one. It's the sigma norm of the error. And what we see is that it has a piece that is this one. So it's saying that, in that term, beta hat is playing no role. It's 0. So beta hat is a 0 on the projection bigger than k. And on the other hand, this term can be small. Here I'm doing some non-trivial work, right? Because sigma k is smaller than sigma L. And sigma k squared can be much smaller than sigma L. Okay, so what we learn from this is that I can have both Vn goes to 0. This is if k, for instance, if k over n is much smaller than 1, is k over n goes to 0. And so this is the condition for Vn going to 0, is that k is much smaller than n. And Bn also going to 0. This will depend, you need, for instance, this piece to be 0, just you need beta to be concentrated on the top k eigenvectors of sigma, aligned to the top k eigenvectors of sigma, and perhaps a bit more, right? So that these coefficients are very small. So top square root of k eigenvectors of sigma. So this is if beta star concentrated on top eigenvectors of sigma. Okay. So this phenomenon, so that this makes sense, or I should. So this phenomenon was discovered, and this kind of these formulas and this formula in a paper by Bartlett. So you can have this with lambda equals 0. Notice. Okay. So you are interpolating your data, but still you are getting the error goes to 0. So this is what we mentioned at the last lecture, and this is the first example of this phenomenon, right? We were mentioning that letting lambda to 0 in low dimension will give you always bad test error bounded away, excess risk bounded away from 0. Instead, in this case, it gives you excess risk going to 0. So this was called. Now, it can go to 0 very slowly, right? For instance, one example in which this work is this one, right? K over n in this case goes to 0, but goes to 0 only as 1 over log n. So by far it's not the optimal rate, right? The optimal rate could be better, but it goes to 0. So this was called benign overfitting, and was proved in a paper of Peter Bartlett, and so it was Peter Bartlett, I think Phil Long, Alex Ziegler, and Gabor Lugosi in some order. Any question? Okay, so this is the first phenomenon, so you need these two things. Now there is so to some extent, I answered Lenka's question, I think, of where the non-zero lambda come from. Did I? But okay, I want to comment a bit more on that. The non-zero lambda star. So I'll give you a simplest example. This was the example that at first when I noticed this, I thought I understood something. So simple example. So this is, let's say, noise in covariance model. So what I mean by this, let's assume the following, that my design matrix Z is some Z0 plus an additional term W, delta times W. Delta is a small coefficient, where these are IAD. Okay, so I take any design matrix and I add to it a little bit of noise. What happens to my ridge regression thing? So we said that there exists an explicit formula for this, that is lambda I n plus 1 over z transpose minus 1 y. And this is an n by n matrix, is really a kernel matrix. We'll come back to this, but this is the kernel matrix. Okay, so I'll call it Kn. I say kernel matrix because it's an n by n matrix whose entry ij is the scalar product, the normalized scalar product between feature vector for data point I and feature vector for data point j. Okay, so this kernel matrix takes the form of the kernel matrix. Okay, let me write it 1 over n z0 transpose. This is the kernel matrix of Z0. And then there is delta square times W transpose plus cross terms. Okay, and let's ignore, for the sake of the argument, the cross terms. Now you can write this piece as 1 over delta square, and there is over n over n. Delta square over n, and then the expectation of this is just P times the identity matrix. And then there is a delta square over n times W transpose minus P times the identity matrix. Okay, or I'll write it like this. Expectation of W transpose. So this is, what is this matrix? This is a matrix that is n by n. Okay, it's symmetric. Entries on the diagonal, or all entries, are basically of order what? Entries with 0 mean and of variance of standard deviation square root of p, right? Because each entry is the product of two Gaussian vectors, standard Gaussian vector of length p. Right? So by the central limit theorem, all the entries are. So this is really very similar to a Wigner matrix. So you would guess, and in fact it's not hard to prove, that the norm of this matrix is square root of n times p. The operator norm of this matrix is square root of n times p. Okay? So basically, this thing is something like delta square times p over n times the identity plus delta square times square root of p over n times a matrix that I call G and as unit norm of order 1 and roughly is in fact it's a V-sharp matrix but is similar to a GOE matrix. So for p over n negligible large, this is negligible compared to this. And so what we get is that the kernel matrix is equal to the kernel matrix 2 of the original model plus p over n delta square times the identity plus smaller stuff. Right? And so what you see is that this term in the definition of p get added to lambda. Okay? So this means that lambda becomes lambda plus p delta square over n. Okay, so the presence of this noise in the covariates acts essentially as a ridge regularizer. So this is the simpler example in which you can see that randomness translates into a regularization effect. This is in fact it's a very old observation. There is a paper by, I think, Chris Bishop in something like New Rips 1991 or 30 years ago or 25 years ago, in which he points out this fact about general optimization, general learning. And in fact, as a method to get regularization, just add noise in the covariates. And there is also a paper that studied this, a more recent paper by Kobach and others that studied this more in detail. Okay, questions about this? Okay, so there is a lot of interesting things happening with this linear regression model, despite it's very old. One thing that you can do apart from this is, of course, look at specific examples. I will not study this in much detail, but let me mention a couple. Why this is noisy? All right, so let me quickly mention a couple of specific examples. I mean, by specific examples, I mean specific choices of sigma and beta star. Okay, so you can take specific choices, plug it into the formulas, and get the behavior of the risk. And so this is just to make a couple of observations. Of course, the simplest example is you take sigma identity, and if you take sigma identity, any beta star is the same, right? Because everything, the formulas are rotationally invariant. Okay, and let's say again lambda equals 0 plus. Then say p over n goes to gamma. Let me not write formula, but just draw the behavior of the risk in this case. So the risk is a function of gamma. So there is a null risk, so this is the norm of beta star square. So this is the risk that you obtain by predicting 0. And the way this behaves is more or less like this. Okay, so this has this characteristic divergence at the point in which the overparameterization ratio becomes 1. That is related to the fact that the matrix Z becomes the condition number diverges at this point. Okay, so this is this pattern. Now, is this kind of curve a good way to think about, or it gives us a good conceptual toy model for overparameterization? Not really, because as gamma increases the number of parameters, but changes also the function that we are trying to learn. Okay, so I don't think, I don't know who pointed out first that you saw this thing, perhaps Advani and Sachs. In this model, and so you could reproduce this double descent phenomenon, but this is not really I would argue this is not really a very satisfying model for how overparameterization, a very satisfying toy model of how overparameterization behave. A more interesting model is the following. So let me call the latent space model. And I'll describe not by giving sigma or beta star, but in equivalent terms. I'll construct the yi as some theta star transpose gi plus xi, and then zij as wj transpose gi plus uij, and then I'll take gi normal 0 id, and then I'll take xi normal 0 sigma square xi, and uij normal 0 1. And those things are independent. Okay? So in other words, there exists a latent space that is d-dimensional, and my true response are a linear function of this latent space variable, and my covariants are also linear functions of this latent space, and these are some vectors. So these are some fixed vectors, and let's say that these are unit vectors. So now this is completely equivalent to this thing if G is normal, right? Because if you fix the theta star and the W, now Z is Gaussian, of course. In fact, Z is Gaussian with covariance sigma, that is W transpose plus the identity, where W is obtained by stacking the Wj. And Y is jointly Gaussian with Z. So there exists for sure a beta star such that this fits my original model. Okay? So this fits the original model, on top of it is Gaussian. But now this is a nice model in the sense that I can vary the level of parameterization without changing the complexity of my function. The function is d-dimensional. I have a d-dimensional function. This is the d-dimensional function. And I'm fitting it by computing features, projecting the original covariates into many different directions. Something that perhaps you wouldn't do in practice, but conceptually starts to be not too far from, I mean, okay, let's put it this way. It's really the simplest model in which I can fix the dimension and then change the level of parameterization. And now if I plot the same curves there, so you can compute everything, and let's say that P over n goes to gamma and D over n goes to some other constant. Let's say 1 over 100. And then, if you plot these curves, you see, and you can find plots. Now things are, okay, you say, okay, if you look at this from far, this doesn't look very different from this, but what happens here that this goes to 0 at large overparameterization. If you choose your parameter properly, while this goes to the null risk of large overparameterization. Right? So this not only conceptually was not the right model, but didn't have an interesting behavior at large overparameterization. You overparameterize a lot, and you reach a trivial behavior. Here you overparameterize a lot, and then you reach 0.
The excess risk that you are talking
So yeah, the excess risk. Yeah, always are. Now, let me point out one thing is that you get this, but then you can learn a lot of other things from this formula. For instance, one thing that you can learn is that if you turn on a little bit of regularization, first this disappears, this divergence disappears and becomes a bump, and then if you add the optimal regularization, this becomes monotone, as you would expect. You add more parameters, this doesn't get you worse, right? If you regularize properly. So these are the brown curves are the curves that you would obtain either if you fix lambda as some value different from 0, or if you take lambda to the optimal value for every possible value of the overparameterization gamma. So this phenomenon is completely due to the fact that you are not regularizing this. So in a sense, this is, I think in this plot, this divergence is the least interesting part of the thing. The interesting part is that these things are going to 0. And the other thing that you can plot is that you can plot the norm of the vector theta star, and you get that the norm of the vector theta star has a very similar behavior to the risk, or a qualitatively similar behavior to the risk. Meaning that this divergence can be interpreted as a consequence of the fact that the model becomes more and more complex as you approach. But if instead counting parameters, you count the norm of the model, then you don't see the non-monotonicity. Okay.
Isn't theta star fixed, actually?
Ah, sorry, this is not theta star, but this is, I got it completely wrong, thank you. This is beta hat lambda. I had both the notation wrong because I confused theta with beta, and then I had conceptually wrong because. Any questions? All right. So this is what we can learn, or most of what we can learn from this linear regression model. And okay, so just let me add one thing. It's okay. This of course fits perfectly with the model that I described before, right? With the benign overfitting computation, because this is exactly a case in which, when you compute the beta and the sigma is a low-rank structure, is an approximately low-rank matrix. Here I'm assuming always D much smaller than P, so it's an approximately low-rank matrix. So the eigenvalues decay. Well, in this case, they have a very special thing. They are constant and then small. And then, if you compute the beta turns out to be aligned with the top eigenvectors, as you see that they both depend on G. Okay, so this structure, this Y, is aligned with the top eigenvectors of sigma. So it's exactly the situation in which you expect benign overfitting from the general theory that I described before. Okay, so this is linear regression. Now we'll talk about kernel ridge regression. So what is kernel ridge regression is really, okay, so why we're interested in it? First, because it's a non-parametric method. And second is because it gives you the limit as the number of parameters goes to infinity of neural networks in the linear regime. So will help us to make more contact, to go towards our goal that to describe generalization of neural network in this linear regime. So I'll start with some background because I don't want to assume that you know about kernel ridge regression, but I will be quite concise. So, okay, what is kernel ridge regression is so we do 1 over n. I'll do square loss, minimize the square loss, and then I add to it a penalty that is a certain norm of the function f. And the norm is defined as, so this is called RKHS norm. And is defined in terms of a kernel K. So to do kernel ridge regression, I have to define a kernel K. So for me, this will be a function RD times RD to R. And the function, okay, so this takes a pair x1, x2, and splits a number k of x1, x2. And this must be a PSD kernel. So what does this mean? It means that if I take any set of points, x1 to xn, and I look at this matrix, so this is an n by n matrix, this must be PSD. So this is what it means that the kernel is PSD. Now, if you look at such a kernel, you can associate to it an operator that I'll write as bold k. So this will be an operator in L2 of P. See, this is a probability distribution on RD, and think of it as the probability, the distribution of your data point to L2 of P. Okay, and how you construct? Well, this is just the integral operator that maps G into Kg that attacks as the value integral Kx x prime G x prime P dx prime. Okay, so this is a kernel. Okay, so as for a PSD matrix, I can decompose a kernel into a basis of eigenvectors. I call the eigenvalues lambda L square. And this will be the eigenfunction that, of course, will form an orthonormal set. Okay. And so what is the behavior of this eigenvalue? Well, one simple remark is that if I look at the trace of k, what is this? This is the integral of kxx pdx. And wow, for most kernels that you write down, so typically k, you take it to be a continuous function. So this is less than some constant. And so this means that the sum of the eigenvalues is finite. The sum of the eigenvalues is finite. So these eigenvalues are, in particular, you can order them. I'll take them all strictly positive, and they go to 0. Okay? Very nice. Okay, so this is everything about kernel. Now I can define the norm, and this is the sum over 1 over lambda L square times phi L f. Okay, so this defines the norm. So, okay, morally, this is f k inverse f. I say morally because k must have can have some 0 eigenvalues. So, but modulo this is what is the norm. Okay, so let me give you an example. The simplest possible example, let's say that Px, P is just the uniform over 0 to pi, the uniform distribution. So my x's are one-dimensional, and they are distributed uniform over the interval 0 to pi. And let's say that f from 0 to pi, okay, just to simplify the example, let's say that my function is complex valued function. So instead of an RKHS over real function, let's do an RKHS over complex functions. And let's say that I take the eigenvectors to be a periodic function with plane waves. And let's say that we take the eigenvalues lambda k square to be 1 plus absolute value of k to the 2s minus 1. So they must go to 0 and must be summable. So you want s to be bigger than 1/2, of course. Okay, and I put the plus 1 just to make it well defined at 0. Right? So this defines an RKHS. Let's look at what is the norm of a function f. What is the RKHS norm of a function f in this thing? So I just applied the definition. So this is sum over L, or sum. Okay, the difference between this and this, of course, that one normally indexes eigenvalues from 1 to infinity. Here, so by natural numbers, here I'm indexing them by integer numbers, not necessarily non-negative, but of course you can reorder them as you want. Yes?
What's the kernel here?
What's it?
The kernel in this example?
Oh, the kernel it is, I can give you the kernel by giving the eigenfunctions and the eigenvalues, right? So the kernel is just this formula. It's something. Actually, you can write it there, but okay, I chose this example in such a way that it's simple to write at the norm. I think it's simple also to write the kernel, at least for S integers, it's simple to write the kernel. But let's write the norm. So this is what is sum over L in Z. So I was saying this is indexed by Z instead than the naturals, or let me call it Q in Z. And then you have the inverse of the eigenvalues, 1 plus Q to the 2s. And then you have the Qth Fourier coefficient of f. Okay, so here some of you are physicists, supposedly, so everybody can do Parseval formula. So this is the integral. So the first part gives me the norm of f square. And the second part, okay, this is for s integer. And the second part is the norm of s derivative of f, the L2 norm of, and this is in dx over 2 pi, 0 to 2 pi. So this is what is the RHS norm. Of course, you can repeat this example in any number of dimensions, but this is what is the RHS norm for this choice of the eigenvalues. This is actually, this norm has another name. It's the Sobolev norm. It's a Sobolev norm. Okay, so RHS spaces generalize certain subsets of Sobolev spaces, but okay, what is important here is that somehow this norm encodes the smoothness of the function f. So a function with a small norm, RHS norm, is a smoother function. Okay, so now there is one last, so far I did 15 minutes. Let's do other 5 minutes about general introduction. I have to tell you how to solve this thing. Right? Here, this a priori is an infinite dimensional problem, but in fact it has a finite dimensional solution. And there are many ways to derive this finite dimensional solution, but I'll tell you the one that I prefer. So how do we solve it? Well, there is something called the representative theorem, but yeah, I don't find it particularly. I think the easiest way to understand it is the following. We expand f in the basis of eigenvector, okay, and solve it for a, right? Now, if you expand in the basis of eigenvectors, it's convenient to define a matrix phi. Is a matrix that each has n rows and infinitely many columns. And each row corresponds to one data point, x1, and is the evaluation of all the basis functions on that data point. So the second row is phi1 of x2, phi2 of x2, etc., and so on. And the last is phi1 of xn, phi2 of xn. So when you are doing kernel ridge regression, it turns out you are just doing a ridge regression with these infinitely many parameters, with this infinite matrix. Okay, so this formula here corresponds to doing the following: computing A as a lambda argmin of y minus phi A square plus lambda A square. So this norm here, what it is? No. Wait, sorry. Now here I have to put the RHS norm, so this will be A d minus 1A, where D is the diagonal matrix that contain the eigenvalues. Right? This is just replacing this thing, right? Because if you multiply this matrix, by A, you obtain the evaluation of f at the n data point. Okay, so this phi times A is just f of x1, f of x2, f of x3, f of xn, and the RKHS norm of f, where in the basis of the eigenvector of k is really A d minus 1A, where A, D is this diagonal matrix. And okay, now we can solve it very easily. So this gives you at is equal to 1. There is no 1 over n. D phi transpose, and then lambda in plus phi d phi transpose. And what is this matrix Kn? Well, its entry ij, it's an n by n matrix, and its entry ij, well, it's rho I of phi, and rho I of phi here. So this will be sum over L lambda L square phi L xi. This is the ith row of this. This is the lth entry of this, and then I column, jth column. So this is the evaluation of the kernel. This is the same formula that we used half an hour ago for the planar regression. We are just applying it to this case. Okay, and this is now you see why I called before this a kernel matrix. Okay, and now this gives you A, and in terms of it you can compute f at lambda, that is the sum over L, and then A lambda L phi L of x, and this now you can write it, it's just hitting this with another phi. So what it gives Kn x dot. Okay, let me write in a minute what is this. Same for transpose, and then lambda in plus Kn inverse, and then y. So this is the solution where this K this is an n by n matrix, and this is the vector with entries Kn. This is K x x1 K x xn. Okay, so now I finished my 20 minutes introduction to kernel ridge regression. Perhaps it's a good moment to stop. And what I'll do is in the next lecture is that I'll talk about what is the risk in this model when we take both the ambient dimension and the number of data points to infinity in various ways. Okay, that's it for today. I didn't ask for questions, apologies.
So right now, Just from this, we can't tell that only n of the a's will be zero, non-zero.
We can tell that n of the a's will be on the y.
Will that turn out to be the case at the optimum?
No, no, not necessarily, right? No. The a's will be all non-zero. I mean, in general, they will be all non-zero. Yeah, so this is not seeking a sparse solution. It's a non-sparse solution. So all of them will be non-zero, and f will be some functions. Yeah. Other questions? Actually, yesterday somebody I don't remember, perhaps after lecture, somebody asked me, I should say this perhaps, you proved us that, with this lazy training, that, okay, this is the ERM0, the space of interpolator. You start at a point, and then you prove that in a small ball around this point, there is an interpolator under some conditions. And then you state a theorem by saying that gradient descent or gradient flow converges to the interpolator. How are the two connected, right? I mean, did you prove the second claim? I didn't prove the second claim. It is a proof that is not much harder than the proof that I showed, but it requires an argument. And basically, the argument consists in showing that dr in dt, you compute the time derivative of the empirical risk, and you upper bound to minus, and then you have here some minimum eigenvalues minus this constant that we define, and then r hat. And, okay, so you write the equation for this, and then at a certain point you do an inequality you control by the minimum eigenvalue of this Jacobian, minimum single value of the Jacobian that we defined. So just to say, it requires a small proof. If any of you, I can show you after the lecture in 5 minutes. But just to clarify that I didn't prove it in the lecture. Okay, that's all. Thank you.